All right, from here we're going to have a little bit of a lengthy discussion on intermolecular forces. First of all, intermolecular means between two separate molecules. So these are not the forces typically holding a single molecule together, although every once in a blue moon we'll see some hydrogen bonding or dipole-dipole forces that are intramolecular, and these are also prominent in peptides, which technically are single molecules. However, most of the time we're talking about two separate molecules, the interaction between them. These are typically much weaker than actual covalent bonds. So take a look at these. We've got hydrogen bonding, we've got dipole-dipole forces, we've got London dispersion forces, and we've got ion-dipole forces. And we're going to take some time at length to talk about each of these. So let's first talk about hydrogen bonding and dipole-dipole forces together. The reason we're going to talk about them together is hydrogen bonding is really just a super duper strong dipole-dipole force. But let's just start with plain old dipole-dipole forces here. So to be capable of dipole-dipole forces, you have to have two molecules that are polar. And my favorite example here is HCl. Chlorine is more electronegative than hydrogen, and so we're going to have a polar bond here. And in this case, that's going to leave the chlorine partially negative, the hydrogen partially positive. So same thing on that other molecule here, it's also polar. And again, the hydrogen partially positive, the chlorine partially negative. And so what you've got here, this dipole-dipole force is the interaction between the partially negative chlorine in one molecule and the partially positive hydrogen in another molecule. And notice this is way weaker than the actual covalent bonds that are holding these HCl molecules together. But this is what you call a dipole-dipole force, and the more polar the molecule, the greater these dipole-dipole forces are going to be. Now, technically, if you look at hydrogen bonding, I really wish they wouldn't have called it hydrogen bonding. Hydrogen bonding is not really a bond. It's much weaker than an actual covalent bond, but they called it that. But it always involves hydrogen, but it's not, not all hydrogens are going to actually be involved in this. So it's only the hydrogens bonded to F, O, or N. I like to think of it as the phone elements. Those are the only H's that are going to be involved in hydrogen bonding. And so in this case, classic example is water here. And we've got OH bonds in two different water molecules here, and that's going to leave, again, the oxygen is partially negative, the hydrogen partially positive in both molecules. In this case, we're going to get the interaction between the lone pair and the oxygen on one molecule. We really focus on the lone pair of electrons there. And the hydrogen that's bonded to oxygen on the adjacent molecule, the partially positive hydrogen here. And that's what we refer to as hydrogen bonding. So you got to have an FH, OH, or NH bond as a pure liquid to be capable of this hydrogen bonding. In this case, we call the molecule that has the H involved the hydrogen bond donor, and this will be much more important actually when you get to biochemistry if you're going there. And the atom that has the F, the O, or the N with the lone pair is the hydrogen bond acceptor. Cool, and that's hydrogen bonding. One thing to note is that if we had some molecule over here like formaldehyde, formaldehyde here is not capable of hydrogen bonding as a pure liquid. And while it has an oxygen, it does not have a hydrogen bonded to fluorine oxygenation. Its hydrogens are only bonded to carbon. So it has the partially negative oxygen. It does not have the partially positive hydrogens, unfortunately. However, it would be able to hydrogen bond with water. So if you mix formaldehyde and water says, hey, I'm supplying the donors, so the partially positive hydrogens, and formaldehyde's got the partially negative oxygen, so all things work out. And so if you're going to hydrogen bond with water or some other hydrogen bond donor, you actually don't need the FH, OH, or NH bond. You just need an F, an O, or an N. But for pure liquids, notice this would imply a mixture, but for pure liquids, you really need that FH, OH, or NH bond. Okay, now let's take a look at London dispersion forces. Some people call these van der Waals forces. You should probably treat those as being synonymous, even though there is a subtle difference, but treat them as synonymous. But I'm going to call them London dispersion forces here properly. And this is a weak, transient, or temporary dipole. The idea is that electrons are in motion, and even for nonpolar molecules, their electrons might be more on one side of the molecule than another at a given instant in time. And as a result, one side of the molecule might temporarily be partially negative, where the other side's partially positive. But this is temporary or transient, and these are generally not that strong. But one thing you should note is that all molecules have these. But for a nonpolar substance, this is all you got. And that's why the most common example we'll talk about this is for nonpolar substances. Now, something like water, which has hydrogen bonding, also has London dispersion forces. But if you've got superglue, why talk about the Scotch tape, so to speak? So water is hydrogen bonding, so the London dispersion forces that it has we usually just don't talk about it too much, but they're there. All molecules have London dispersion forces. Now, these typically depend on three things. So a higher molecular weight, a larger surface area, and greater polarizability. And atoms get more polarizable as you move down on the periodic table. But all three of these result in higher London forces. If we look at three alkanes here, so here we've got C4H10, here we've got C5H12, and here we've got C6H14. So all of these are nonpolar. If you notice, they all have either carbon-carbon or carbon-hydrogen bonds, which are all nonpolar. Without any polar bonds, these are just simply nonpolar molecules. So the only intermolecular force they're going to have is London dispersion forces. But if you notice, as we move to the right, we're getting a greater molecular weight as well as a larger surface area. And as a result, the intermolecular forces are increasing as you go from C4 to H10 to C5 to H12 to C6 to H14, just increasing London dispersion forces as a result. So now that we've talked about hydrogen bonding, dipole-dipole forces, London dispersion forces, now we'll figure out why we've been talking about this to begin with. So it turns out that intermolecular forces, how sticky molecules are, if you will, affect some of the bulk properties of a substance. So higher intermolecular forces lead to higher boiling points, higher melting points. Those are the two most important for our discussion, but also a greater viscosity, a greater surface tension, and the one thing that's lower is a lower vapor pressure. So these are some of the things that intermolecular forces affect, and most commonly we'll be talking about that in the context of boiling points and melting points for organic chemistry. So if you're ranking boiling points, the most important one here, first thing you want to look for is network covalent solids. Those have the highest. They're not anything we're commonly going to see in organic chemistry, but truth be told, they could ask you. And these are things like diamond or graphite or silicon dioxide, which is quartz. Very few and far between things you have to know that are network covalent solids. You would be much more likely to be tested upon this in a general chemistry course than an organic chemistry. But second on the list is ionics. So, and this will show up every once in a blue moon, but also not the most common one, but this one you might actually see in your organic chemistry course, much more likely than a network covalent solid. And then after that, finally, if you're ranking boiling points, the next thing you want to look for is hydrogen bonding. So, and then dipole-dipole forces, and then London dispersion forces. So if you notice, the strength of the intermolecular force here, or the interparticle force, is increasing as you go up. Now, one thing to note, we have here London forces are the weakest, but again, we said earlier that London forces increase with increasing size and molecular weight, surface area, polarizability. If you've got dipole-dipole forces, those are going to beat the London forces if all molecules are similar in size. However, if your molecules aren't all that similar in size, the larger one's going to have enough London forces that even if it's less polar, it'll still have the greater overall intermolecular forces. Now, the difference in size has to be very, very significant for a nonpolar molecule to be, have overall greater intermolecular forces than something with hydrogen bonding, although that'll happen on occasion as well. But any kind of significant difference in size, and even a nonpolar substance that's larger will have larger intermolecular forces than a polar molecule that's significantly smaller. So let's look at some comparisons we might make here. If we look at some comparisons, first one here, between the two compounds here, or two substances, which one has the higher boiling point? So we first and foremost realize that the first one here is ionic, showing up right here as the second strongest force affecting boiling points, whereas the next one here has an OH, and that's going to give it hydrogen bonding, but that's nowhere near ionic bonding here. So acetic acid, I don't know what its boiling point is, but I would assume it's probably not too different than water's, maybe a little higher than water's. But this ionic compound here, it's over 800 degrees Celsius. It's a significant difference in boiling point here, and so our ionic compound has the higher boiling point by far. All right, let's take a look at the next example, number 2 here. So in the first one, we've got an OH bond, so we're going to have hydrogen bonding. And in the second one, this bond right here is polar, so we're going to have dipole-dipole forces. These two molecules are very similar in size, similar in molecular weight, but this is the one that's got hydrogen bonding, and so he's going to end up with the overall higher intermolecular forces and the higher boiling point. All right, let's look at the next one here. So number 3 here. In the first example, we've got something polar. That carbon-fluorine bond is polar, where in the second example, we do not have any polar bonds as well, and this substance is nonpolar. And being nonpolar, the only thing it's going to have is London dispersion forces, sometimes symbolized LDF. This guy over here, though, is going to have London dispersion forces and your dipole forces, which I'll abbreviate D/D. So it looks like, oh, this one should be greater, but if you recall, Dipole-dipole forces only win the day here if they're very similar in size, and these are not. This compound on the right, even though it's nonpolar, has a significantly greater molecular weight and a significantly greater surface area than the one on the left. And as a result, he actually is going to have the overall higher intermolecular forces and the higher boiling point. So again, polarity only wins the day over a nonpolar molecule if they're very similar in size. If they're not similar in size, just pick the larger one. All right, finally, last comparison on the page here. So we already kind of compared these in terms of intermolecular forces. Now we're just going to compare it in terms of boiling point, but we've got C5H12 on the left. We've got C6H14 on the right. So the compound on the right has a little higher molecular weight. It's also going to have a little higher surface area, and as a result, it has the greater intermolecular forces. In this case, they're both nonpolar, so only London dispersion forces, but greater intermolecular forces and the higher boiling point. All right, now we've got to talk about something that's unique to organic chemistry here, and that's to talk about the effect of branching on both the melting point and boiling point. So if we look here, branching is only really going to come up when you're talking about isomers. And if you look at these two compounds here, this is C5H12. And if you look at this one as well, he's also C5H12. So, and that's the only time branching really needs to be discussed to any significant degree. If you've got two different compounds that are not isomers, whichever one is larger and has larger molecular weight, just kind of go with him as having the greater intermolecular forces. But when you've got two isomers, that's when branching is going to be relevant here. And so if we look at these two compounds, we've got the first here on the left, C5H12 pentane, is completely unbranched. And then we've got 2,2-dimethylpropane on the right, which is completely, about as branched as you could make it, in fact. And so in this case, you can see what happens to boiling point. And for unbranched, it's 36.1 degrees Celsius, but for the branched, it's 9.5 degrees Celsius. And so the branch structure has a lower boiling point. And the reason it has a lower boiling point is because it has a lower surface area. So it's the more compact structure. And so that lower surface area means it's going to have lower London dispersion forces, and the lower London dispersion forces are going to lead to an overall lower boiling point. So cool, that's the effect on branching. It lowers the boiling point. So, but we see it's going to have the exact opposite effect on the melting point, and we've got to explain this. So if you notice pentane here, again, unbranched, melting point or freezing point, same diff, negative 129.8 degrees Celsius, but significantly higher melting point for the 2,2-dimethylpropane. So this is weird because 2,2-dimethylpropane has the lower boiling point, but now we're seeing it has the significantly higher melting point. So in this case, branching actually raises the melting point. So the boiling point goes down due to branching, but the melting point goes up due to branching, and we have to explain this. So, and the idea is that this more compact, as well as sometimes symmetry plays a role, structure means it fits into a crystal more easily. And fitting into a crystal more easily is going to favor that solid phase more than the liquid phase at more elevated temperatures. And so you might actually not have to cool this thing down to such a low temperature to convert it into a solid. So its freezing point, which is the same as its melting point, is going to be higher as a result. So in this case, it's not about the intermolecular force, it's about how well it packs into a crystal. And the more compact and more symmetrical structure packs into a crystal more easily, and therefore is going to have a higher melting or freezing point. Okay, one thing to note about this branching here, I've gone to both extremes here. I've gone to a completely unbranched structure here and then compared it to one that's completely branched, and that's when this comparison holds truest. So however, when you start comparing, differing degrees of branching, like slightly branched to slightly more branched and stuff, it turns out there are a ton of exceptions here. This is the most likely context you're going to see branching, but truth be told, some people teach this exact opposite way and say, oh, no, branching does the opposite. And the problem is that there's really no absolute true trend here. So when you come and compare boiling points and melting points and stuff like that. So if you're comparing something completely unbranched and something that's very branched, that's when this holds true. So the very branched will have a lower boiling point, but a higher melting point than the thing that's completely unbranched. So, but if you start having things that are slightly branched, you're going to definitely see some exceptions to this trend. Just an FYI. So if we look at the question on the right here, the question is who's got the highest boiling point and then who's got the highest melting point. So first off, we should just look at these and say, okay, this is C5H12. This guy's C6H14. And this one, 1, 2, 3, 4, 5, 6, is also C6H14. So right off the bat, if I'm looking for the highest boiling point and melting point, branching is not the first thing I should consider. I should just consider, okay, who's got the greatest molecular weight? So these are all nonpolar, so only London dispersion forces. So greatest molecular weight, greatest surface area. And right off the bat, he loses this battle because compared to the other two. Now these two are isomers, and we can see the difference is a difference in branching, but again, branching is only something to consider when they are isomers, as they are in this case. And so in this case, if I want the higher boiling point, I actually want the one that's less branched. So that's the middle one here. So he's got the higher boiling point. So, but the one on the right here is the more branched one, and if I'm looking for the higher melting point, I actually want the one that's highly branched as the one on the right. And so this one's going to have the higher melting or freezing point. So hopefully we can see the difference of branching here. I like to think of branching sandwiches that, as long as you're comparing, again, highly branched to unbranched, branching brings down the boiling point, brings up the melting point, so making the liquid exist over a narrow range. So hopefully that's clear. All right, the last area we're going to talk about the relevance of intermolecular forces with solubility. And the governing principle in solubility is that like dissolves like, and we mean in terms of polarity. So if two, actually, let's just do the examples here. So we want to know which of these is the most soluble in water, and so we got to ask ourselves, what is water like? Well, water is very, very, very polar here. I've got the structure in blue. So it's very polar. So if I want something to dissolve in water, I want it to be very would So the greatest solubility would be which of these molecules is the most polar. Now every one of these molecules has an OH, so they're all capable of hydrogen bonding, and that makes them have something in common with water. They have a portion of the molecule that's very polar. So however, every one of these molecules also has a region that's nonpolar that water doesn't really care for. That's not like water. And so if we look to the same degree, every one of these molecules is like water with one OH bond. And the question though is which one is the most like water? And the key is it's going to have the smallest region that's not like water, and that's that first one. And so this first one is the most like water because it's the least not like water, if you will. It's got the smallest nonpolar region, so that's going to be the one that's most soluble in water. Now the second question here is which is the most soluble in hexane. Now I've given you the formula here for hexane, and even if you didn't know his structure, you'd see, oh, being made of all carbon and hydrogen, it's not going to have any polar bonds, and it's simply going to be nonpolar. So, and being nonpolar, then I just want which of these is the most nonpolar. So it's the same three compounds, and again, every one of these has a region of the molecule that's very polar with an OH bond being capable of hydrogen bonding. The question then in this case is not which one has the smallest nonpolar region, but which one has the largest. And so obviously I'm circling all the nonpolar regions. Obviously this one to the far right has the biggest region of the molecule that has low polarity or nonpolar in this case, and that's going to be the one that is going to be the most soluble in hexane. So it turns out he was the least soluble in water, since he's the least polar, so out of the three, but he's the most soluble in hexane, since he's the least polar. Cool, and that's how solubility works. So one thing you should understand about the solubility as well is that this idea that like dissolves like. The idea is that when something dissolves, when a solute dissolves in a solvent, you have to kind of pull the solvent molecules apart to make room for the solute molecules. But you also have to pull the solute molecules apart so they can spread out throughout the solvent. And so you've got to break apart the intermolecular forces of both the solvent and the solute. And the idea is that you get an increase in solubility if the new intermolecular forces you form between the solvent and the solute are comparable or greater than the ones you had to break. That's where you get an increase in solubility. And that's why like dissolves like. Hopefully the intermolecular forces you're making are comparable to the ones you're breaking. And that's going to be most true when your solute and solvent are most alike in terms of polarity. All right, the last intermolecular force I want to talk about here are what are called ion-dipole forces. And I haven't really mentioned them up until now, and I had them separate from the other three intermolecular forces on the original slide for a reason. So ion-dipole forces are only ever going to be present in a mixture. The other three intermolecular forces could be present in a mixture, but also could be present in a pure substance. And being as we were using them to compare the boiling points of a bunch of pure substances, that's why we kind of group them together. But in this case, ion-dipole forces only can be present in a mixture because it implies you've got something ionic mixed with something polar. And the most common example is when you dissolve an ionic compound in a polar solvent like water. So we can kind of see how this works here. So if I dissolve salt in water, NaCl in water, so you'll see the sodium ions, being positively charged, get surrounded by the partially negative oxygen ions of the water molecules, and we form these ion-dipole interactions. So whereas the chloride ion, being negative, is going to be interacting with the partially positive hydrogen ions of the water molecules. So, and these interactions diagrammed in red here, those are the ion-dipole interactions. And these ion-dipole interactions generally are stronger than even hydrogen bonding. Now, the truth is I can come up with some very strong examples of hydrogen bonding and some weak examples of ion-dipole forces, and it would be vice versa. But in general, most ion-dipole forces are stronger than even hydrogen bonding. But again, the key here is they're not ever present in a pure substance. They're only going to be present in a mixture.